Earlier in this chapter, we looked at some special products when we multiply binomials. And now we're going to try to factor those special products when they've already been multiplied and give us a polynomial. So this is going to be a matter of pattern recognition. So remember that if we took a binomial a plus b and squared it, we ended up with the first term squared plus 2 times the first term times the second term, 2ab, plus the second term squared. And if we had a minus b squared, we ended up with the same thing except that the middle term had a subtraction, so minus 2ab instead of plus 2ab. So when we find a perfect square that we're trying to factor, what we want to look for will be, is that first term, is the a squared or x squared or whatever it may be, is that a perfect square? Is the last term a perfect square? And then is the middle term twice the product of the square root of that first term times the square root of the second term? So in other words, if a and c, remember our coefficient of x squared and the constant, if those are both perfect squares, then we want to check if b is twice the square root of a times the square root of c. And that can be either a positive 2 times those or a negative 2, either way. So for example, when we have x squared minus 8x plus 16, x squared is a perfect square, 16 is a perfect square. The square root of 16 is 4, the coefficient here is 1, and the square root of 1 is 1. So if you take 1 times 4, you get 4. Notice that negative 8 is negative 2 times 4. So in other words, this is a perfect square right here, and it factors into x minus 4 squared. Minus because we have a negative 8x here. Okay, and one that will be probably a little bit easier to spot is the sum and difference. Remember when we took a plus b times a minus b, we ended up with only two terms. That first term squared minus the second term squared. And we call that a difference of two squares. So if you see a binomial and there's a subtraction, check to see whether those are both perfect squares. If they are, then you know how to factor that into a sum times a difference. So if we take x squared minus 9, notice the first term is a perfect square, that's equal to x squared. 9 is a perfect square, that's equal to 3 squared, and we're subtracting, so this factors into x plus 3, x minus 3. Alright, let's look at some examples. So first of all, we want to start out by factoring each polynomial. So we look and we see x squared plus 10x plus 25, we have a trinomial, and we notice that this is a perfect square, so this is equal to x squared, and 25 is a perfect square, that's equal to 5 squared. And then we check and we see that 2 times x times 5 is equal to 10x. And notice that's our middle term. So in other words, x squared plus 10x plus 25 is equal to x plus 5 squared. And again, this will become more familiar to you as you do more of these problems. Okay, number 2, we have 9x squared minus 24xy plus 16y squared. Notice that this is a perfect square. This is 3x in parentheses squared. And this is a perfect square. This is 4y in parentheses squared. And if we take 2 times 3x times 4y, we get 2 times 3 is 6, times 4 is 24xy. And notice that here we have a negative 24xy. So in other words, this is a perfect square, this time involving subtraction. So 9x squared minus 24xy plus 16y squared is equal to 3x minus 4y, oops, get that parentheses there, squared. Alright, number 3, 16x squared minus 49y squared. Here we have a difference of squares, because this is equal to 4x in parentheses squared, and 49y squared is equal to 7y squared. And so we're going to end up with a sum times a difference. So 16x squared minus 49y squared is equal to 4x, that first square root, plus that second square root 7y, 7y, times the same thing except subtracting, so 4x minus 7y. Okay, number 4, remember the whole point of all this factoring is to be able to solve equations. So let's look at this and see if this will factor. So we already have a quadratic set equal to 0, so that's good. We want to see if this will factor. So we notice that this is a perfect square. 4x squared is equal to 2x squared. 9 is equal to 3 squared. So if we take 2 times 2x times 3, that's equal to 12x. And notice that is what we have in the middle here. So that tells us, let's see, we started with 4x squared plus 12x plus 9 is equal to 0. But this will factor into 2x plus 3. Quantity squared is equal to 0. And so then we can take the square root of each side to undo the squaring, and we end up with 2x plus 3 is equal to 0. Now subtract 3 from each side to get 2x equals negative 3, and then finally divide by 2 to get x equals negative 3/2. And notice here that we only get one solution, and that's because we had a binomial squared rather than two different binomials being multiplied together. Okay, number 5. 25 minus 30r equals negative 9r squared. So we have a quadratic here because we have an r squared term, and remember that in this case we want everything over to one side. Now, generally speaking, I would say we really would like that leading coefficient to be positive. So I'm going to move this negative 9r squared over to the other side by adding 9r squared to each side. And then I would suggest you write in standard form. So start with the highest exponent, the largest degree. So we have 9r squared, and then minus 30r. Make sure you keep that negative sign with the 30r, plus 25. And this is equal to 0. Okay, so we have a quadratic. It's already set equal to 0 now. So now we want to see if this will factor. And you might notice, oh, 9r squared is a perfect square. That's equal to 3r squared. And 25 is equal to 5 squared. So what happens when we take 2 times 3r times 5? We end up with 6r times 5, which is 30r. And notice that is our middle term. We're subtracting 30r. So that tells us that when we have 9r squared minus 30r plus 25 is equal to 0, this factors into 3r minus 5 squared equal to 0. And again, we can take the square root of each side, so we get rid of the squaring. And again, we're only going to end up with one solution as a result. So we end up with 3r minus 5 is equal to 0. So that means we can add 5 to get 3r equals 5, and then divide by 3 to get r equals 5/3. Again, please just leave that as a fraction. So we're set. Okay, number 6. 9v squared minus 23 equals 13. We actually have a couple different ways to solve this one. So remember that in general, when you see a quadratic, you want everything pulled over to one side. So one method will be to go ahead and subtract 13 from each side. So subtract 13, subtract 13. We end up with 9v squared minus 36 is equal to 0. And then notice that we have two perfect squares here, and we're taking the difference. So we have the difference of two squares. This is equal to 3v squared, the 9v squared is, and of course 36 is equal to 6 squared. And so this is equal to, let me rewrite that, 9v squared minus 36 equals 0. We can factor that into 3v plus 6 times 3v minus 6 is equal to 0. And so we have a product equal to 0. That means either 3v plus 6 equals 0 or 3v minus 6 is equal to 0. So subtract 6 from each side and we get 3v equals negative 6. Divide by 3 to get v equals negative 2. Or add 6 to each side to get 3v equals 6. And divide by 3 to get v equals 2. So it's either a negative 2 or a positive 2. Now another way to solve this would have been, and this is a little bit of a heads up into a section you'll see in chapter 10, when we don't have a v term here, we have a v squared, we have a constant, but there's no v term. Another option is to move the constants to the other side of the equation. So we could have also added 23 to each side, and then we would end up with 9v squared equals 36. Then we could divide by 9 to get v squared equals 4. And then when we take the square root of each side, now we want, because we have a positive number here, we actually want plus or minus the square root of 4, which of course, as you know, is equal to 2. So v is equal to plus or minus 2, which is exactly what we got using our first method. Okay, so you're welcome to use either one of these methods. I think the benefit of using this method at this point in time is so that you get practice seeing the difference of two perfect squares and factoring that to solve. So, good luck, and as always, enjoy.